So now that you know how to draw a dot on the screen, I can get back to how my Etch-a-Sketch program works. So let's look at first what I've done in the Etch-a-Sketch program. I have defined my port IDs. So these are my port IDs for the VGA, which match exactly to the port IDs for the VGA. Here's your 909192 in the rat wrapper. So if you make any changes to port IDs in the wrapper, you need to make sure you make the changes in the assembly code as well. So I have the port IDs for the VGA, then I have the port IDs for the 7 segments and LEDs, and then I have constants defined to represent the 4 keys that I care about. So the W, the A, the D, and the S. Now, how do I know that these are the right codes for W, A, D, and S? Well, if you go to the internet, you can Google Nexus 2 board reference manual. There it is. There it is. I've already pulled it up. And in the reference manual, it gives you lots of information about the PS2 port, the USB port, the keyboard. There's all sorts of stuff in here, a little bit about how the VGA works, how I've explained some of that. So this is a really good reference manual. Anyway, we're going to look at the keyboard right now. So here's a picture of the keyboard, and each of these numbers are in hex, and they represent the scan code that you receive when you hit that key. So as you can see, my W, A, S, and D are 1D, 1C, 1B, and 2, 3, which match what I have written right here. Now I also have this interrupt count of 3 because when you hit a key, you will actually get 3 codes coming from the keyboard. The first code that you're going to get is the key code itself, but then when you release the key, you will get an F0 followed by the key code again, and that is explained to you right here in this paragraph, that when a key is released, you get F0 followed by the scan code of the release key. And also, if you wanted to use the arrow keys or maybe some of the extended keys, go ahead and read this section in the manual to figure out how that gets coded from the keyboard. Okay, so then I have my PS2 addresses right here. The next thing I have done is I've commented for myself what I've used different registers for. Now there is actually a .def directive that you can find in the beginning of the RAT assembler manual where you can do something like define a name for your register. So if I was always using the register R6 for color, I could create color reg and define it as R6. And therefore, everywhere in my code where I would have wanted to write R6, I could just write color reg, and that can make your code a lot more readable. For my case, I didn't do that because I felt I could keep track of all of these registers. But if you end up using more registers, it might be useful to define them and use the actual word instead of the register number. Now, I'm not quite sure if I need an equal sign here or a comma or something, so definitely look that up in the RAT assembler manual. Okay, so what happens in my code is the first thing I do is I need to draw a dot at the origin of the VGA and initialize all of my registers to their starting values. So what I'm doing here is my R1, I've enabled interrupts. My R1 is my interrupt count, which is going to count if I've gotten 3 interrupts from my key. Then I'm going to set my origin for the dot. Remember that the Y direction can have numbers from 0 to 29, so half of that is 15, which is why I'm giving the value of hex F. And the X direction can go from 0 to 39, and half of that would be decimal value 20, which is hex 14. So I've moved these into registers R7 and R8, which I'm calling temporary Y and X. Then I've copied those into R4 and R5, which are used for the x and y for the draw dot function. And then I've decided what color I want to draw at the origin, and I put it into R6. And then I have R18, which I use for debug, and R19, which I use for interrupt counting, and then I go ahead and call draw dot. So here we go. We're initializing our registers. You can see it happening over here. When I call draw dot, if I want to go into that function, I'm going to click on the blue arrow. There we go. Now this is looking a little off, so let me just start it again. Clicking on the blue arrow to go into the function. And so we already explained this function. And it goes like so. And then it goes and returns. And look, I'm going back and forth in the main loop because no interrupts have happened. So let me cause an interrupt to happen. Now it jumps to the interrupt vector. Interrupt vector calls the interrupt service routine. What happens in the interrupt service routine? Well, my debug, I've made a 0. Now, notice I could have taken this out of my example because I just threw in these LEDs to debug here and there, but I don't currently need them. So I've added 1 to my interrupt count, which you'll see show up in R19. Then I compare that with 3 to see if I've generated 3 interrupts. If I have, I'm going to see what key did I actually press. But if I haven't gotten 3 interrupts yet, I'm going to just process data return. And what I'm doing in the process data return, I'm not exactly sure about. But what I'm doing is I'm clearing a PS2 flag inside a register of the keyboard controller. So what I'm actually doing is I'm setting this bit in the PS2 control register, and then I'm clearing the bit in the same register. Now, like I said, I'm not exactly sure if that's necessary. But to find out a little bit more about that, you can go into the peripherals keyboard folder and go ahead and read the README about how that might work. Okay, so we are going to return from the interrupt. And now we're back in main. We need another interrupt to occur. We go back to my ISR. We still have not reached the count of 3. So we're going to return. And back in main forever and ever. We hit it again. Okay, we branch back to my ISR. Now the count is 3. So when the count is 3, I'm going to go to my check keyboard routine. In my check keyboard routine, I was doing this debug thing to say, okay, yes, I got inside this check routine. So I made my R18 a 1, and then I outputted that value to the LED so I could actually see a light to say, yes, Bridget, you got inside this check keyboard area of the code when you ran it on the board. Then I'm going to clear my interrupt count, which was 3, and now I'm going to set it back to 0. And then I'm going to go ahead and read in what was on the keyboard. So I read in the key code from the keyboard, so this gets it directly from the keyboard and puts it into register R2. And then also for debug purposes, I'm outputting what I read from the keyboard onto the 7-segment display so I can just see, okay, what key did it actually read. Then I'm going to compare that value with the value that I wanted for up. And up was the W value, the 1D. So let's see, if I do an in, here in the simulator I can simulate what I pushed by the keyboard. So I'm going to go ahead and push and say that I got a 1D. So when I compare R2, which is 1D, with up, which is 1D, I should branch to my move up routine. So what move up wants to do is increase, or rather decrease, the value of my y coordinate. So if I look at my move up, here again this was just for debug to say, okay, I got into the move up routine. What I'm doing is I'm going to subtract 1 from my R7 value, which is holding my temporary y, and then I'm going to copy that into R4, which is what I need to have it in for the draw dot routine. So I've subtracted 1 from y because I want to move up in the display, and remember the upper left of the display is 0, 0. So I only need to subtract 1 from the y. I move that into R4. R8 is still going to be the same because that's my X. It didn't change if I'm moving up, and I move that into R5. Then I'm going to call draw dot again to draw that dot on the screen. And instead of going into the draw dot routine by hitting the blue, I can just skip over it by hitting the green. And then I'm going to process the data return. So after I finish moving up, I'm going to jump back down to the end where I'm going to clear my PS2 register to say that I have serviced my key, and then I will return from the interrupt. And this goes on and on and on, and then I get 3 more interrupts. And each time I get an interrupt, what my check keyboard routine is doing is it first compares with the up. If it got an up, it'll go to the move up routine. Then it compares it with the down. So if it didn't get it up, maybe it got a down. If it got a down, it goes to the move down. Then it compares with the right. Then it compares with the left. And then it compares with F0. I didn't really need to do that because I'm not going to be moving anyway. I think that was also part of my debugging process. And so in each of these, we already discussed that move up, we're subtracting 1 from the y coordinate, and move down, guess what? You're going to be adding 1 to the y coordinate. In the move left, you're going to be subtracting 1 from the x coordinate, and in the move right, you're going to be adding 1 to the x coordinate. So once you finish this whole code, before you run it on your RAT machine, RAT CPU on the Nexus board, you want to actually walk through it all in the RAT simulator to make sure it's doing what you want it to do. So I'm pretty happy with my code. When I'm all done with it, I make sure I assemble it. And when I assemble it, you'll see right now it's 6:05 p.m. I can check to see that in my assembly folder of my Etch-a-Sketch project, I have a program which has 6:05 p.m. and this program is directly connected to the program in this project. So if you wanted to be absolutely sure, you can remove this from the project and then you can add your new source of the program directly from the assembly so you could check the time on it. Then once that is all done, you generate your programming file and you check it on your Nexus board. Now back to the debug again. So it's really hard to check what's working on your code and what's not. And what I do to go about debugging is I start putting outputs to the LEDs everywhere where I want to check something. So if I wanted to make sure that my code actually got to the interrupt service routine, I could put an LED output here. If I wanted to make sure that my code actually got to this loop, I could output an LED here as I did. So that's one really nice method for actually checking if it's working on your board. Another method is to actually look at the signals on the scope, which you might want to do so. In 133, some of you had practice using the logic analyzer, so you could output signals directly to your PMOD connectors and see when they're changing. But my recommendation is start with my project, copy in your RAT CPU, and make sure it works with my Etch-a-Sketch code. And then once you have that working, then you can go ahead and start writing your own assembly language program. And this one, as you can see, it was 6.3 in hex. So 6.3 in hex is, I'm gonna be lazy and use the calculator. 6.3 in hex is what in decimal? It's 99. So my code was only 99 lines long of actual program code. I'd like you to write something that's at least 300 lines long. And the best approach is to figure out what different functions you need, make them individually, test them out first in your RAT simulator before actually trying it on your Nexus board. Good luck!